In this lesson, we will explore the concepts of arithmetic and geometric series and their applications. We're going to start with the arithmetic series. So before we start, we need to know, what is a series? A series is the sum of the terms in a sequence. Every sequence has a corresponding series and vice versa. So for example, we have an arithmetic sequence 1, 3, 5, and 7. Notice each term is separated by a comma. The common difference here is 2. To get from one term to the other, you would add 2. An arithmetic series would be adding all the terms in that arithmetic sequence. So it'd be 1 plus 3 plus 5 plus 7. So as you can tell, in an arithmetic series, the terms are separated by the addition sign. So an arithmetic series is the sum of the first n terms of an arithmetic sequence. So adding up all the terms in an arithmetic sequence gives you the arithmetic series. So note, S subscript 1 means the sum of the first term. In our case, subscript 1 would equal to 1 because that's the first term. S subscript 2 means the sum of the first two terms. So we take the 1 plus the 3, which is 4. S3 means the sum of the first three terms. So S subscript 3 is equal to 1 plus 3 plus 5, which is 9. S subscript n means the sum of the first n terms. So you would just add depending what term number you are wanting the total sum of. So there is a formula that we use to come up with the sum of an arithmetic sequence. And this formula goes as such. So S subscript n is equal to n over 2, so divided by 2, times bracket 2 times a plus n minus 1 times d, where n is the term number, a is always that first term, and d is that common difference. Now, a modification of that formula is whether if you're given the first term of the sequence as well as the last term. In that case, the formula is S subscript n is equal to n divided by 2 times bracket a, that first term, plus the last term, t subscript n. Okay, looking at example 1, we need to determine the sum of the first 30 terms of the arithmetic series 42 plus 41 plus 40. So in this case, we're only given that first term. We're not given the last term. So we're going to use the first version of sum of an arithmetic sequence. So we're going to say we need to figure out the sum of the first 30 terms. So we do know n is equal to 30. We know that the first term is equal to 42. We also know to get from one term in the series to the next, we're subtracting 1. Subtracting 1. So that common difference, -1, no, because we want the sum of the first 30 terms, n has equal to 30. So in our case, we can say S subscript 30 is going to equal to, again, n divided by 2, which is 30 divided by 2. 2 times a, which is 42, plus n minus 1, so 30 minus 1, times d, which is -1. Okay, the one thing that we always have to follow in math is BEDMAS. So let's, again, within the brackets, we're going to make sure we follow BEDMAS. We can simplify that because that's just reducing our fraction. And 2 times 42, we know is 84, plus 30 minus 1, which is 29, times -1. So I should have used. Okay, so again, following BEDMAS, we're going to say S subscript 30 is equal to 15 times 80, 29 times -1, which is minus 20. I don't know how that became 80. That was 84. Okay, so S subscript 30 is equal to 15. If we took 84 minus 29, which is 55, 15 times 55, which is 825. So we can say, therefore, the sum of the first 30 terms is 825. Okay, moving on to example 2. We have determined the sum of the following arithmetic series. Now notice it's -4 minus 10, minus 60, minus dot, 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 minus 94. So in this case, we are given the first term, and we are given the last term. In this case, we can look at the second version of the sum of the arithmetic sequence. So we can say Sn is equal to, notice we're missing something. We don't know actually how many terms are in this sequence. We know that the first term is -4, and we know the last term is -94. But in this case, we still need to determine how many terms. Now, we can use our knowledge of arithmetic sequences to help us. We know, again, we're going to use the step 1, use arith sequence to determine the number of terms in the series. We need that first, otherwise we can't figure out the sum of the following arithmetic series. So we know A is my first term, which we know that there's a common difference. The common difference would be -10 minus -4. So the common difference would be -10 plus 4. So the common difference is -6. So you're subtracting 6 to get from one term to the other. Okay? We also know what the last term is. So Tn is equal to -94. We can use that information to determine n, the number of terms. So we know the formula for arithmetic sequence is a plus n minus 1 times your d. So we're going to say -94 is equal to -4 plus n minus 1 times -6. So -94, simplifying, we're going to expand that, is equal to -6n plus 2, bringing that over, -96 is equal to -6n. Dividing both sides by -6, we know n is equal to 60. Okay, so now we know how many terms we have. We're then going to use that to figure out the sum. So the sum of the first 16 terms, again, we can use the modified version because we are given the first term and the last term. So we can say n divided by 2. I'm going to say a plus t and n. So in our case, because we know n is 16, we're going to say s subscript 16 is equal to 16 divided by 2, a, which is -4, plus the last term, which was -94, s subscript 16, 16 divided by 2, which is 8, -4 minus, which is -98. And if we take 8 times -98, we get -784. Okay, so I forgot to indicate, but step 2, use sum of an arithmetic sequence formula. Yep. So the sum first in this case, which is a good example, we need to first figure out how many terms were in the series before we can figure out the sum. Okay, moving on to example 3. We have for the arithmetic series, so 6 plus 9 plus 12 plus 15, we want to determine the 20th term. So in this case, again, that common difference we still need, which is plus 3 plus 3 plus 3. Okay, so looking at A, okay, we need to know the sum of the oh, we just want to know what the 20th term is. So in this case, because we only want to know what the term is, we are going to use arithmetic sequence to determine what that term is. So we're going to say n minus 1 times d. Okay, so we know n is equal to 20, a is equal to 6, and that common difference is 3. So T20 is equal to a, which is 6 plus 20 minus 1 times d. The 20th term is going to be always following BEDMAS, so deal with the brackets first. 20 minus 1, which is 19 times 3. We know 19 times 3 would be 57. So the 20th term, 6 plus 57, which is 63. Okay, now we're going to determine the sum of the first 20 terms. So again, B, we have sum of the first 20 terms. We know n is equal to 20. Now notice we're not given the first term and the last term, so we're going to use that first version of sum of an arithmetic sequence formula. So we know a is still equal to 6, d is still equal to 3. So just a reminder, as subscript n is equal to n over 2, 2 times a plus n minus 1 times d. So the modified version can only be used if you're given the first term of the series and the last term. So in this case, 20 divided by 2, 2 times a, which is 6, plus 20 minus 1 times d, which is 3. Now simplifying again, keeping in mind, I'm going to say 6 times 2 is 12, plus 19 times 3. Now again, sum is going to equal to 10, 12 plus 9 times 3, 19 times 3, sorry, which is 57. No need for square. So we only have one bracket. Following BEDMAS, of course, always work out and simplify brackets first. So we have 12 plus 57, which would be 69. Sum of the first 20 terms would be 690. Okay, moving on to word problems. We have example 4. In an amphitheater, seats are arranged in 50 semicircular rows facing a domed stage. The first row contains 23 seats, and each row contains 4 more seats than the last. How many seats are then in total? So we know there's a total of 50 rows. We know the first row contains 23 seats, and each row contains 4 more seats than the last. So with that, we're going to break down that information, and maybe we need a little bit of a visual. So that first row has 23 seats. The next one over has 4 more. So if we took 23 plus 4, that would be 27. Next one, we can add another 4. So 27 plus 4, which is 31. And then we get to the end. We don't know how many seats are there, but this is the 50th row. Okay, so we don't know how many seats are there, but we know each additional row. So the first row had 23, the next one was 27, 31. We're going to get all the way to the 50th row. What we do know then is A is equal to 23. We know that. That common difference, because we said each row, we add another 4. So we do know that. We need to know then how many seats are in that last row. And the only way we can do that is to use the arithmetic sequence formula. Okay, so we know T at n is equal to A plus n minus 1 times D. We know that there's a total of 50 rows, so we need to know how many seats are in that 50th row. So to do that, we do use this 23 plus 50 minus 1 times that common distance of 4, because that'll tell us how many seats are in the 50th row. So d of 50 is equal to 23 plus 49 times 4. So we take 49 times 4. You can say 23 plus 49 times 4. That's 196. Yeah, 50 is going to be 219. So we know there are 219 seats in that last row. Okay, with that, then we can find the sum. We're going to use the modified version. So as that 50 is going to equal 2, n, which is 50, divide that by 2. Remember, it's times the first term, which is 23, plus the last, which was 219. So 25 times 23 plus 219, which would be 242. 25 times 242, which is 6,050. So again, this is a word problem. So we do have to make sure we answer the question. So how many seats are there in total? Therefore, there are a total of 6,050 seats in total in the, let's make sure I am stated. EM. Okay, so keep in mind with the word problem, we want to have that therefore statement. Looking at example 5, we have Samantha deposits $128 into her bank account. Each week, she deposits $7 less than the previous week until she makes her last deposit of $9. Find the total value of her deposits. Okay, so we know her first deposit, so T1 is equal to 128. Okay, she deposits $7 less each week. So then that means 128 minus 7, which is 121. Third deposit would be less 7, which is 114. And then she keeps going until we get T at n, which is equal to 9. Okay, so we want to find the total of all her deposits. Well, we want to know how many deposits were actually made. We don't know that. We don't know n. So we are given that A is equal to 128. D is equal to negative 7. And then we're also given that T at n is equal to 9. So we can use this information in order to determine how many deposits were made. We just know that her final deposit that she made was $9. So with that, we can say, using the formula for an arithmetic sequence, we can say n minus 1 times d. We can say 9 is equal to 128 plus and minus 1 times d, which is negative 7. We need to know what n is. Okay, using our mathematical skills, make sure when you're expanding with those signs, so negative 7n, negative times a negative is a positive. So 9 is equal to 128 plus 7, which would be 135 minus 7n. I'm going to bring that 135 over, so 9 minus 135 is equal to negative 7n. So we know 9 minus 135, which is negative 126. We need n by itself. So we know n is equal to 18. Okay, so now that we know that she's made a total of 18 deposits, we can figure out the sum of the total value of her deposits. Now again, we have the first, so we have T1. And we also know now that we can change that to T at 18. Okay, we have the first and the last. We can use the modified version as sum of arithmetic sequence. We can say n, which is 18, over 2 times first term, which is 128, plus the last, which is 18. 18 divided by 2, which we know is 9. 128 plus 18. Oh, why did I get the 18 from? That's supposed to be the last term. So the last term is supposed to be 9. So we take 128 plus 9, which is 137. So S18 is equal to 9 times 137, which is 1,233. Again, it is a word problem, so we want a proper therefore statement. So find the total value of our deposits. Therefore, the total value of Samantha's deposits is $1,233. Notice the dollar sign is up front. Perfect. Okay, so now that we've focused on and learned about the arithmetic series, we're going to move on to the geometric series. So a geometric series is the sum of the first n terms of a geometric sequence. So given the geometric sequence 2, 8, 32, you can see that common ratio is 4. 2 times 4 is 8, 8 times 4 is 32. So therefore a geometric series would be 2 plus 8 plus 32. So the sum of a geometric sequence would be as subscript 0 is equal to a times r, so that common ratio to the exponent of n, the number of terms, minus 1, all over r, which is the common ratio minus 1. Or, again, the simplified, or depending if you're given the first and last term, as subscript n is equal to the ratio times the last term, t subscript n, minus a, which is your first term, all over the ratio minus 1. And in both cases, r cannot equal to 0, because that would leave that geometric sum of this geometric sequence undefined. Okay, so look at example 1. We have determined the sum of the first 8 terms of the geometric series. So if we want the sum of the 8 terms, we start with the first term. Okay, the common ratio, again, just like a geometric sequence, we would 64 divided by 6. So the common ratio in this case is 4. Okay, we're asked to find the sum of the first 8 terms. That means n has to equal to 8. And of course, we're given the formula, so we step it right into the formula. S subscript 8 is equal to a times r to the exponent of n minus 1 all over r minus 1. Always following BEDMAS, so we'd work within the brackets. Be 6, 4 to the power of 8, which is 65,536 minus 1 all over 3. Now we can reduce this. So 6 divided by 3, we know it could be simplified to 2, working in the brackets. Subtract 1 would be 65,535. I'm multiplying that by 2. The sum of the first 8 terms of a geometric sequence would be 131,070. Now, looking at B, same idea. The first term is A, which is 6. Their common ratio, we take negative 24, divide that by 6. The common ratio in this case would be negative 4. And n, of course, is the same, which is 8. Because we want to know the sum of the first 8 terms of that geometric series. So we're going to then substitute s at 8 is equal to a, which is 6. This time I put in brackets negative 4 to the exponent of 8 minus 1 all over negative 4 minus 1. Okay, simplifying because it is a even exponent would be the same, minus 1, except for the denominator, negative 4 minus 1, which would be negative 5. Okay, subtracting 1, always following BEDMAS, so we're simplifying the brackets. Negative 78,642. Okay, looking at example 2, we have for the geometric series 5 minus 10 plus 20 minus dot, dot, dot. A, we want to determine the 7th term. So with that in mind, when we just want to know what the term is, we're going to use the formula for a geometric sequence. So we know that the first term is A, which in our case is 5. That common ratio would be taking that negative 10 divided by 5. So R is equal to negative 2. Okay, and we also know that N in this case is 7. So again, just to remind us, A, R, N minus 1. That is the formula for a geometric sequence. So we want to know the 7th term. So it'd be A, which is 5, negative 2, 7 minus 1. So for the 7th term, okay, always following BEDMAS, negative 2 to the power of 6, which would be 64. 5 times 64. So the 7th term would be 320. So we want to determine the sum of the first 7 terms. So in this case, we would know that first number, and we'd also know the last number. Okay, so we can use the modified version of the sum of the first 7 terms. Okay, so that means S at 7 is equal to, again, the common ratio of negative 2 times the last term, which is 320, right, minus my A, which was 5, all over, okay, R minus 1. So the common ratio, negative 2 minus 1. Okay, always following BEDMAS, negative 2 times 320, which would be negative 640 minus 5 all over negative 3, and negative 645. Divide that by negative 3. So the sum of the first 7 terms would be 215. Negative divided by negative. Okay, let's double check that. We have 6. No, we could have used, again, the original formula as well. It doesn't really matter. Either of the two can be used specifically with what information you're given. So in this case, when we're given the first term and that last term, because we did give that 7th term, then we can use either or. However, if you're not given that last term, then you only can use the first version. Okay, so determine the sum of the following series. So this is a perfect example. We have the first and we have the last. Okay, but we don't know how many terms we have in the series. So again, you always have to determine that first. You need to know how many terms you have before you get the sum of all of them. So let's do step 1. Determine number of terms. So Tn is equal to AR and minus 1. The first term we know is 5. That common ratio is negative 15. Divide that by 5. So the common ratio is negative 3. And we want to know what N is. So that's okay, but we are given that T at N is equal to 3,645. Okay, so we know 3,645 is equal to A5, the common ratio negative 3, and minus 1. We divide this side by 5. Divide that side by 5. So we have 3,645 divided by 5, which is 729. Negative 3 to the power of n minus 1. So again, when we were solving exponential equations, we have to make sure that those bases would be the same in order to properly compare them. So we would take negative 3 to what exponent gives you positive 729? That would be 6. When we were solving exponential equations, when the bases are the same, therefore we can say, therefore, 6 has to equal to n minus 1. Bringing that over, 6 plus 1 is equal to n. So n is equal to 7. Okay, so there's a total of 7 terms in this geometric series. Now to determine the sum, step 2, determine the sum. We would say, again, I'm going to use both just so you can see that it doesn't matter what version of sum of a geometric sequence formula you use, you will get the same sum. So let's use, I'm going to write them both down. So we have a to the n minus 1 all over r minus 1, or it doesn't matter which one you use, you'll still get the exact same answer, minus a all over r minus 1. Okay, so in this case, we know a value is 5, r is negative 3, all to the power of n, 7 minus 1, all over r, which is negative 3 minus 1. Okay, so we always want to follow BESMAX. Negative 3 to the exponent of 7 is negative 2,187 minus 1, all over negative 4. Negative 2,188. 5 times negative 2,288 times 5, negative times 5 divided by negative 4 would be 2,735. Now again, we don't have to ever do this 2 times. I just want to show you that it doesn't matter which one you use. Actually, I shouldn't say it doesn't matter which one you use. The final answer will be the same, but the information provided has to be there in order to use the second version. You need the first term and the last term of the series in order to use this version of sum of a geometric sequence. So S at 7 is equal to R, that common ratio, which is negative 3, times our last term, in this case, which was 3,645. We're going to subtract our first term, which is A, which is 5, all over R, which is negative 3 minus 1. Okay, so 3 times 3,645, which is negative 10,935 minus 5 all over negative 4, which is 940. Divide that by negative 4, which again will equal the exact same, 2,735. Okay, so again, you never have to do both. I just wanted to show you it doesn't matter which version you use, you will get the same sum. So we can say, therefore, the sum of the series is 2,735. Okay, looking at example 4, we have a catering company has 11 customer orders during its first month. For each month afterwards, the company has doubled the number of orders in the previous month. How many orders in total did the company fill at the end of its first year? Okay, so during its first month, that would represent A is 11. So we can say A is equal to 11. Then each month afterwards, the company doubled the number of orders. So that means that common ratio would be 2. So we know doubling means R is equal to 2. So then it says, how many orders in total did the company fill at the end of its first year? Now notice we're talking about years, but in this case, the unit is months. We have to convert years to months. So we know n is going to equal 2. In 1 year, we know there are 12 months in 1 year. So to convert that, those cancel out. So n is equal to 12. So we need to know what is the sum or the total amount of orders that the company filled at the end of its first year. So that's after 12 months. So we know S at n is equal to a times r to the power of n minus 1 all over r minus 1. So at the end of the first year, we're talking about the 12th month. A is 11, or which is 2 to the power of 12 minus 1 all over r, which is 2 minus 1. Okay, always following BEDMAS. We know 2 to the power of 12, which is 4,096, minus 1 all over 2 minus 1, which is 1. 4,095. So therefore, 11 times 4,095, which would be 45,045. So we can say, remember, it's a word problem. How many orders in total? Therefore, the company filled a total of 45,045 orders at the end of its first year. Okay, looking at example 5, we have at a fish hatchery, fish hatch at different times, even though the eggs are fertilized at the same time. The number of fish that hatch were 2, 10, 50, 250, all the way to 3,906 and 250. If the pattern continues, click the number of fish hatched. Okay, so we need to know how many numbers are in this pattern. Okay, so we know that the first number of hatch eggs was 2. We know that common ratio we can determine, which is 10 divided by 2. And we also know the final number of hatching, so 906, 250. Okay, so but we don't know total number of fertilizations happening. So we need to figure that out. We need to know what n is. So we know we can use geometric sequence formula AR to figure that out. So we know 3,906,250 is going to equal to A, which is 2. The common ratio is 5 and minus 1. We're going to divide both sides by 2. So we have 1,953,125. Those cancel out. 5 to the exponent n minus 1. So as we learned earlier, in order to compare and solve these exponential equations, we need to express 1,953,125 as a base of 5. So 5 to what exponent? That would be 5 to the exponent of 9 is equal to 5 to the exponent n minus 1. So once the bases are the same, we can say, therefore, the exponents are equal as well. So 9 is equal to 9. N minus 1, bringing over that 9 plus 1 is equal to n. So 10 is equal to n. Okay. So we then take Sn is equal to A times r to the exponent of n minus 1 all over r minus 1. So in order to determine the total number of fish hatched, we know as at 10 is equal to the first term, which is 2. That common ratio, again, of 5 to the exponent of 10 minus 1 all over 5 minus 1. Okay, again, I can't stress always following BEDMAS. 5 to the exponent of 10, which is 9,765,625 minus 1 all over 4. 2, that cancels out, so we're going to say 9,765,624. I'll divide that by 2, which is equal to 4,882,812. Okay, so the total, therefore, the total number of fish hatched is 4,882,812 fish.